Okay, Chem 1110 students, now we're on to the second video of Chapter 2. So in the first video, we talked about the various subatomic particles, and now we're going to talk about the atoms that they make up and how they are arranged in the periodic table, which is a very important tool for the chemist. So we know that atoms can be identified by the number of protons and neutrons they contain, and in fact, those quantities have been given names. So the atomic number, which is known as Z, is the number of protons in a nucleus. Because atoms are neutral, that's also the number of electrons there are in the atom. And we need to remember that the protons determine the identity of an element. So any nitrogen that has an atomic number of 7 has 7 protons. Doesn't matter how many neutrons it has, it is still nitrogen. And that brings us to the next topic, which is the mass number, which is given the letter of A, and that's the total number of protons and neutrons. And those exist in the nucleus, so together those are called nucleons. And this is one way that we write elements to be very specific about which element and kind of atom we're talking about. You have an elemental symbol, and those are things like C for carbon, O for oxygen, He for helium. At the upper left, we put the mass number, which is the number of protons plus neutrons. Lower left, we put the atomic number, which is the number of protons. Now, the fact of the matter is that most elements have more than one isotope, meaning they all have the same atomic number of protons, but they can have varying numbers of neutrons. And here's an example of hydrogen. You have hydrogen that just has 1 proton. You have deuterium that has 1 proton and 1 neutron, and tritium that has 1 proton and 2 neutrons. Those things are generally produced in atomic reactions, but these isotopes have very similar chemical properties, so they form the same kind of compounds, very similar reactivities, so they'll often make very similar compounds. So water is H2O, but heavy water, which is generally in the blanket around a nuclear reactor, is going to be heavy water, where a deuterium is used instead of a hydrogen. You can have T2O, which is even heavier water made with tritium. Okay, so I have an example here where we want to write the numbers of protons, neutrons, and electrons for each of these following species. And so what we're going to look at is at the top, we have the atomic number, the upper left, that tells us the number of protons and neutrons. At the bottom left, we have the atomic number, which tells us the number of protons. And so by manipulating those two, we can get the number of neutrons. And we know that atoms are neutral, so the number of electrons equals the number of protons. So when we go to look at chlorine 35, we know the Z is 17, so there's 17 protons. That means there's 17 electrons. Our mass number is 35, so 35 minus 17 tells us there are 18 neutrons. So if we look at chlorine 37, it still has 17 protons and 17 electrons, but now that mass number is different. It's 37, so we take 37 minus 17, and it has 20 neutrons. So that is an isotope of chlorine 35. When we look at the potassium, we know potassium's atomic number is 19, so there's 19 protons, 19 electrons. We take that mass number of 41, subtract 19, so there's 22 neutrons. So that's a case where we didn't have the atomic number. We had to go to the periodic table to know that potassium's atomic number was 19. We can also look at this last one, which is carbon 14. We talk about carbon-14 dating. It's because it's a natural isotope of carbon, and it's usually written as 14 in the upper left-hand corner with a C. From the periodic table, we know carbon's atomic number is 6, so there's 6 protons and 6 electrons. And if we take that mass number, 14, subtract the 6 protons, that means there's 8 neutrons. So I just want to point out that a lot of the slides have this think about section, which helps you verify that you did the problem correctly. So you will probably want to take a look at those. All right, the other thing we need to talk about is the average atomic mass. First off, we use a special unit, and it's called the atomic mass unit. Atoms are extremely small, so therefore talking about them in terms of grams would be very difficult. So the AMU, or atomic mass unit, is defined as 1/12 the mass of a carbon-12 atom. And so that is basically the mass of a proton or the mass of a neutron. And whenever we stop and think about the fact that most elements have isotopes which have additional neutrons, and therefore they have different masses, if we're just trying to talk about carbon in general, we've got to look at its average atomic mass. And so when you look at the carbon-12 isotope, its isotopic mass is 12 because that's the one we use to define it. And it's the one in greatest abundance. It's at 98.93%. Whereas carbon-13 is has a mass of, as you can see, 13.003355 atomic mass units. So that is, it's more than just one more because neutrons are slightly bigger than protons, if you remember. The natural abundance is extremely low. And I didn't list carbon-14 here. And so therefore you probably realize that carbon-14 is existent at even lower amounts. And so at the bottom I show the calculation of that average mass for carbon. All right, so now we're going to talk about the periodic table. And the periodic table is useful to chemists in that it shows us a relationship between various elements. And it is arranged so that elements that have similar chemical and physical properties are grouped together. And interestingly, this can be achieved by ordering these elements in atomic number. The other thing I want you to look at on this slide is just what is contained in each box. So at the top you have the atomic number, and you can see they go in order of atomic number. That's the number of protons. You have the symbol, you have the name, and you have the average atomic mass listed. All right, so we're going to talk about how this periodic table is useful to us. And the first thing is that these elements are arranged in periods, which is the horizontal rows, in order of increasing atomic number. Now, new rows are formed, and as you can see, it's something of a bit of an odd shape, but they are, a new row starts in order to keep these elements that have similar properties together. So I just want to show you sort of some categorization of the elements with the way the periodic table is arranged. So first off, we have metals. They are the light green. They are good conductors of heat and electricity, and you can see that that makes up the majority of the elements that we know about. Non-metals are in blue. They are very poor conductors of heat and electricity, and in fact you can see a lot of these are gases like helium and neon and oxygen. Obviously those atoms are very far apart, so they don't conduct electricity well. And then the final group are shown here in orange, and they are called metalloids, and they are between the metals and the non-metals, so they have some intermediate properties between the two. Remember, we said that metals are good conductors. These metalloids are often called semiconductors because they only conduct electricity partially, and that makes them very good for the computer industry, as we know. All right, vertical columns are known as groups, and these have very similar chemical properties. And in fact, we restart the rows in order to make sure that the groups have similar chemical properties, and we've given those groups names. So the first column are the alkali metals, very similar chemistry. The second column are called the alkaline earth metals. You do need to know these titles. Then we jump way over to the third from last column, and this is the group 6A. Sometimes this is called the oxygen group, but that has a formal name of the chalcogens. Next to that, we have the halogens, very important group, very active chemistry. And finally, the last group are called the noble gases. And these things hardly react at all. And that's where they got the name noble. Because, you know, in years gone by, the nobility didn't react, or shall we say intermarry, with commoners. And so they didn't take part in the kinds of reactions that most people did, and thus the name noble gases. The other big group here that is sort of lumped together is that big middle section, and those are called the transition elements or the transition metals, and we will talk about their chemistry later in the course. All right, you can move on to the next video.